Yo, Thomas,
Yeah, man.
could you flick up in the back
Yeah.
so we can get some content for the Instagram? All right, I'll go ahead and get us started. Thank you all for coming today. So, again, my name is Franco. Really excited for today's presentation. Let me. Okay, so today, what we have done for you guys is the content we're going to go over for modern portfolio theory is literally what we are going through in our CFRM 501 course right now. That is the content that us as graduate students are currently going through. Not only are we doing that, but we're also going to go a bit ahead of that. We're going to go a bit ahead in the math and in the programming. All right. Now, thankfully, what I've done for you guys today is I've managed to boil it down into a palatable 20-minute presentation for you all to follow along, see what's going on. And we have code for you guys to implement this as well. So you can give this a shot. So the code's right here. It's in the Google Colab. So under the meeting content, what I'd like you guys to do is you're going to need to download all of those files. Let me give a demonstration live. Oh, admit. So when you open the code will look like this. What you'll need to do is in this file browser, you'll need to download the files that are all in the Discord content. There's like 5 of them. And then you drag them all right here. Okay. If you do not have experience with Google Colab before, every time you load into a runtime, you need to load in your files every single time because it opens up a new runtime. So make sure you do that. This stuff is the training data that we're going to use for the stocks. So how it's going to work is I'll be going over the mathematics of what's going on, and then I will tell you guys where in the code this is so you can execute it, test it out for yourself. If you have any questions, we have some helpers walking around. Jackie will be able to help out with any specific Python questions if you have them to getting the code running. Okay, well, what exactly is modern portfolio theory? Is there an antiquated portfolio theory? Is there an ancient? Well, in 1952, Harry Markowitz published in the Journal of Finance what we define today as modern portfolio theory. The main idea is that the risk and performance of an investment should not be assessed in isolation, but rather in the context of a portfolio, right? And this means that a diversified portfolio's systematic risk combines different assets with varying correlation with one another with less risk than the sum of its parts of the investment. Therefore, for a given investor's risk amount determined by the investor, we may produce a portfolio that provides the greatest expected return and vice versa. So portfolios optimized for the greatest amount of return given any level of risk will lie on a boundary known as the efficient frontier, which we will plot today. And this risk tolerance is determined by the individual investor. Okay, well, what are returns? Returns measure the change of value in an investment. In this lecture, we're going to be going over continuously compounded returns, which are logarithmic given by this formula. So under the data preparation and return section of the code, if you run those modules, you're going to load in the data from the stocks that we have. We have 4 stocks. I think the data is from like 2011 to 2020. But what you're going to do is you'll be calculating you'll be plotting the stock prices, and you're going to calculate and plot the returns for each of the assets. So we're going to go over what is known as the mean or expected return. Recall or consider, if this is your first encounter, the expected value we define for a random variable as the sum of the product of the outcomes and their probabilities. What does this mean? Well, let's say I have a dice roll, right? And I'm going to roll this dice I equals hella times, right? So for I equals hella, if we're looking very far out in the horizon, right? What's the long run average outcome of the dice rolls that I will be producing? So in order to get that for a dice roll specifically, we take each value that the 6-sided dice has, 1 through 6. We multiply it by its probabilities, and each of them is a 1/6 chance, and we sum them all together. So for a dice roll, after rolling a dice hella times, the long run average should be about 3.5. Okay. So we can set up our portfolio returns in this same manner, such that if we sum up the averages of our returns multiplied by the weights of each of these returns for these assets, we can get the expectation or the long run average outcome of the average of our returns. You can see why we're using this specific choice of words. Okay, so we can treat our portfolio returns as a random variable, thus giving us an expression of our expected portfolio returns. Now, if you reference in the code, there's going to be a section for mean, which calculates the mean of each asset or the returns, and you'll be able to see how the returns are calculated and plotted so we can get the long run averages of them. So from the mean, we can get something called the variance and the standard deviation. Again, very briefly, if this is a refresher for you or if this is your introduction, the variance measures how much the data points are spread and dispersed from the mean. So we have our mean, right? We have the long run average outcome of the returns of our portfolio. Well, the variance is going to tell us qualitatively how much the dispersion is around this mean. You can see right here, the xi is each individual data point. The mu is the mean we calculated previously. So the variance is just the sum of all of the differences from the mean, plus some square and some inverses. So historically, about 30 years ago, we used variance and standard deviation to quantify measures of risk in our investment. So if there's a greater dispersion from the mean of what we're looking at, then there's a greater risk in that investment because there's a greater potential that the stock could perform above or below this mean. Well, with the variance mean, we can calculate the covariance. So if two variables tend to show similar behavior, they'll increase or decrease together, then the covariance is positive. If one stock goes up while the other goes down, then the covariance is going to be negative. It's given by this mathematical formula, but all you need to know is that covariance and correlation determine, how's it going? The covariance and correlation will determine how much a asset performs in relation to one another. And you can reference covariance and correlation, and you compute the correlations of these assets. So our correlation coefficient specifically is the covariance over the product of the two variances. And this is a visual representation of what's going on. You can see with a higher positive correlation, the two assets will perform more and more similar. And with a negative perfect correlation, they perform exactly opposite of one another. So let's create a portfolio now. Suppose we want to create a portfolio where we invest in 4 different stocks. Okay, you have Microsoft, Johnson & Johnson, JP Morgan, and ExxonMobil. As an investor, we can choose how much of our portfolio to put in each one of these stocks. We can put all of it into Johnson & Johnson. We can put all of it into Microsoft. We can put 25% of our assets into, or 25% of our portfolio into each of the assets. All right, keep in mind, none of this has anything to do with our initial investment. Rather, we're allocating the proportions of our portfolio against one another. So this is independent of how much money we actually start with. If you go to the portfolio optimization section in the code and you run it, for a given strategy, a different ratio of different assets, we can get a resultant risk and expected return. Well, if we have different risks and expected returns for different ratios of assets, let's just randomly generate 10,000 of these strategies and see where these means and these variances will end up. So what you guys are looking at right here is modern portfolio theory. I'll take a little bit to let everyone catch up in the code, but for any given portfolio, right, depending on how you choose to allocate your resources or the proportions of the stock, you'll get a different variance for your portfolio, and you'll get a different expected return. So what we can realize here is that, okay, Let's say I am not that risky of an investor. My investment risk tolerance is a bit lower, so I'm right here, right? If I have this portfolio right here, then what that tells me is for the same amount of risk that I have, I can reconstruct this portfolio to tolerate the same amount of risk, but have a higher long run average, higher expected return. So if I'm right here, why would I be here when I could have the same amount of risk and have a greater expected return? So what we see is for a given amount of risk, there exists a maximum value or a maximum expected return for a portfolio. What we see here is we get this top of the curve right here. This curve is our efficient frontier. So that tells us for any given amount of risk, there exists an optimal allocation for the portfolio such that the return is at its maximum value. We can also work backwards, right? Let's say I want to have an idea of how much return I want in a portfolio. Well, then I'll just base it on how much returns I have. Thus, if I approach it that way, based on how much returns I can expect to get, I can paint an idea of the maximum amount of risk I need to expect to incur in order to have a portfolio which may get that much returns. So for any given amount of risk, I have a question.
Can I have a question about the previous slide?
Yes.
So we have most of the return with the minimized risk, that red lines, but doesn't it also mean they are very likely to be overbid?
Does anyone in the audience want to help pitch in?
Well, there's not really like modeling here. What do you mean by overbidding?
So that's the return over risk based on the past data, right?
Mm-hmm.
But we are trying to find the strategy that's gonna work not only in the past but also in the future, right? Mm-hmm. But what I mean by the overbid is that if we are just trying to find that such too good strategy, it might work only in the past but not in the future anymore. And I think it's going to be very likely for the very top lines, I assume.
There's no time horizon on this. This is all for one portfolio on the same day. The only difference is the allocations we have. So we haven't looked at any time horizon yet. We haven't considered. This is all based on the present value of the returns that we've calculated and the variances and covariances and correlations of each individual asset at this particular time.
Okay.
Does that help?
Yeah.
Okay. We'll get there, don't worry. So for any given amount of risk, we can maximize return. For any given amount of returns, we can minimize our incurred risk. So every day, the optimal weights of the portfolio will change, right? Let's say tomorrow, Microsoft announces Windows 12. It's going to be insane. Everyone's going to be like, wow, this is a Windows 12. This is crazy. Tomorrow, the weights are going to go up, right? Or let's say Johnson & Johnson's competitor releases Baby Lotion 2. And all of a sudden, Baby Lotion 1 just is destroyed. All right, no one wants to buy Johnson & Johnson because it's outdated. So every single day, the optimal weights of these portfolios are going to change because individual properties of each stock will determine its behavior. So how do we ensure our portfolio remains on this efficient frontier over time? Well, one way we can do it is to optimize our portfolio looking backward. All right. So we'll compute the optimal weights of each stock using the past 40 days, right? But then every 7 days, we'll rebalance the portfolio such that when we reassess it, we'll have a new allocation of how the portfolio should be at that given day. So that tells us how much of the stock to sell in one area and how much to buy in another one, right? So every 7 days, we'll change the allocation of our portfolio such that we can keep our risk the same and we'll have the maximized expected return, or we can, again, work to minimize returns. So in the code, this is backward-looking portfolio optimization. It should be able to run just straight up. Once you run it, you'll see the steps of the code reallocating itself and your returns. So if we plot it, you'll end up at this graph. This is the growth when investing dollars in each asset. This is the time. This is the portfolio amount. So you can see if you invested in any one of these stocks, that's how much the value of the portfolio has changed over time. But using this backward-looking portfolio optimization, this purple right here is reflective of how much we'll make if we invest in this optimized portfolio. All right. Does anyone have any questions from there about the code or anything? Yes.
So on the x-axis is 0 to 80. Is that like days?
Yep, that's days since we begin the strategy. So like 40 days into the strategy, like every 7 days, we would have reallocated based on the optimal weights. And this portfolio is representative of what the returns look like having reallocated.
You stop reallocating after day 40?
No. That was just for a reference. So we're looking 40 days back into the past, but then every 7 days we recalculate the weights. And then as we do that, we'll have continuously adjusted as we're moving forward. Good question. Anyone else have anything else? Here's the problem. We're looking backward, okay? If the time horizon's that way and I'm being pulled, I'm trying to like guess how I'm being pulled by looking backwards at my path, right? How do we solve this? We look forward, okay? If we need to determine what direction we're going, why would I look backward to do that? Well, I can do it by looking forward instead. As opposed to predicting returns of the past, we predict returns of the future. Well, then you might ask me, then how am I going to predict the future? That's like predicting the future in finance is like what everyone tries to do. Well, what we can do is I can set my present a bit into the past so that the present's here, and then I can look at the future, which is already predetermined because it's the future of the past, and I can train a model that will learn the future as we move forward. So instead of training our model based on performances of the past, we are going to train our model based on performances of the future of the past, which is the present. So we take a few steps back and we try to optimize forward. Well, how do we get it to predict the future? Well, Amazon, I have no idea what I'm looking at here. Would you like to? It gets worse, guys. It gets worse. So this is what a long short-term memory model is in neural networks. Do not confuse it with a short long-term memory model. They are two completely different things. If you use one and mix it with the other, you will get widely incorrect results. Amazon, would you like to briefly go over the long short-term memory model for us, please?
Yeah, Amazon, let's go.
So in this model, we have X here. I think X here is an input to the LSTM. And I'm not sure if it's C or it's like this output to this model, right? And in this model, we have two layers that we consider. The first is CT, and another is HT. And these CT and HT are changed with time. And you can think these two parameters as something like the memories of the model. So in each step, we update the memory of the model. We train the model so that it can manage memory so that it can optimize the outputs. And yeah, so in this model, we have some like some of this that can select what memory to remember and what to forget. And that is the LSTM, obviously.
Okay. So we take a step back. We ask ChatGPT to explain this to us like a 12-year-old. This is an introduction to neural networks. Basically every single like bolded term or like image on the slide in itself can be a 15 to 25-minute presentation. So this is all very surface level. This is meant to get you conceptually sped up to what's going on. I encourage you, everything's annotated, so if you want to read more on the slides in your own time, to focus on one particular area, everything is going to be very, very rigorous and really insightful. So, how do neural networks work? Step one, we set up the network, all right? Imagine we're trying to find the perfect y equals mx plus b, right? We got a bunch of predicted b's and a bunch of predicted m's. We set it all random, right? We feed our data points through, and as they pass through each individual node's B is going to change a little bit. Each individual node's M is going to change a little bit. So as we feed it through a bunch of times, it's going to start to pick up like, oh, this is what the M should be. This is what the B might be, right? So the data is going to pass through each layer, transforming each of these weights and biases through what is called an activation function. So once data reaches the output layer, this is what it thinks the M and the B are going to be in your neural network, okay? And at the very end, we have the loss function. Since we're predicting the future, which is the present, we know what it's supposed to be, so we can give the neural network a frame of reference to how wrong or right it actually is. And as it learns how wrong or right it is, it'll put this back into the network, and it'll say, okay, like, I'm starting to get the hang of it. Like, I'm starting to predict things. So each of these tests are known as an epoch. As you go through the forward approach, you can see in one of the lines of the code, you will go through and run this neural network to go through the epochs. You can set how many epochs that you go through to train the model. I think originally it was set at like 4,000, which took like at least 40 years on my computer, which is a non-trivial amount of time. So I invite you to change it down to a lower number, such as 5, so it wouldn't take the entirety of your undergraduate and graduate career. So once we've finished all of this, going through all of the epochs, we give the network the new data it hasn't seen before, which is the present trying to predict the future. And from there, we can evaluate its performance. So there are broadly speaking, there are two kinds of neural networks. There are feed-forward and recurrent neural networks. The long short-term memory model is a recurrent neural network. And what this means is that we emphasize an aspect of memory. So like Amzin said, it'll take the time to think, okay, this was useful. This wasn't useful. So as it learns y equals mx plus b, it takes a little bit of what it's learned to feed it through and affect the neural network. This is really good for sequences where order and context matter in predictions, time series. So one issue with recurrent neural networks is that the loss function that we mentioned earlier, the gradients, have issues, okay? Over time, they might go to 0. We might end up overfitting the model too much. Or they might explode. We might get it wrong and wrong and wrong over time. So the loss function is going to get too big. So our long short-term memory model is an additional module that really emphasizes that it should remember or forget pertinent information. So as we feed it through with the stock data, there's an additional model in the LSTM that'll say, okay, this is super important. Like this was useless for the data. So it'll start to get better over time in trying to predict it. So in the code, we have a full LSTM implementation. So you can go through, it should be ready out of the box. I think the command is like Alt F9 to run everything at once on Google Colab if you want to. But this long short-term memory model is going to predict the stock returns. So as I showed you earlier with the diagram, these are each of the stock prices. And when you get to this part in the code, when this graph is produced, this is our present, and this is our future of the past. And what we've done is, based on the stock data for each of them, we put our neural network, we put the stocks through the neural network. And as opposed to looking back at what the returns are going to be, or as opposed to looking back at what the returns were, we can now look at what the returns might be, given our LSTM. So once we've gotten there, at the very end, this is again the growth when investing $1 in each asset. And the purple is the backward-looking portfolio, but the red is our forward-looking portfolio. Okay, so this is all of the assets with the portfolio, and on the right is the comparison between the backward portfolio and the forward portfolio. Okay, so what we see is even with this few lines of code that we have in our Google Colab, if you look at the forward portfolio in the short-term horizon, like the first 40 days, the forward portfolio is outperforming the portfolio that was backward looking. So having employed these machine learning techniques, big data, artificial intelligence, right? We realize that, hey, we can make a portfolio that's expected returns will perform better in the short term than we would have looking backwards, right? The model we have is really simple. It was like 5 epochs, but you can see, even though the backward portfolio, actually no, yeah, the forward portfolio basically across all metrics is outperforming our backward portfolio, and this is modern portfolio theory. What's next? So with this code, you can change the individual stocks, see any other stocks you want to look at. You can change the time periods. This is only like 2011 to 2020, I think. So you can fit it in with whatever you want. If you see risk_level anywhere in the code, that shows you, that is your individual risk preference as an investor. So if you were to change this value, you can see one of the lines in the code will produce your efficient portfolio based on your given amount of risk. So you can change the risk level, and you can see where your portfolio changes based on how your risk changed to beginning. So all this code is ready out of the box. You can download it right as is. You can put it on your GitHub. The long short-term memory model unit of this presentation was very abbreviated. All of those slides are very in-depth, very expansive content. If that's something you wanted to learn more in, that's in itself a very arduous endeavor. So does anyone have questions in the meantime? We just networked our neurals. How's it feel? Okay.